All right, let's jump in and start talking about Chapter 2. In Chapter 2, we really start digging into some physics. Chapter 2 is all about describing motion in one dimension. Chapter 1 was just kind of a setup. Hey, where are we going? Where are we coming from? Chapter 2, we're going to dig in and really start talking about some physics. We're going to start with motion in one dimension. And we're going to jump off from where we left off in Chapter 1, which is talking about motion diagrams. So recall that a motion diagram can be made by basically superimposing images of some event. And it can give you a sense of the motion, but it's not super effective as an analytical tool. So even though it can give you a sense of the motion, and it starts to take this idea of motion and turn it into an abstract representation that we can talk about, it's hard to do much analysis on it. And so what we really need to do is take what we've learned from motion diagrams and take it one step farther. We're going to turn those motion diagrams into position versus time graphs. And that's going to really enable us to start to use some analytical mathematical tools to understand this motion. So let's just take an event like a student walking to school. And we could make a motion diagram for that student walking to school, as is done right here. What can we see here? Well, recall that if these dots are all equally spaced in time, then we can tell relative speed by comparing how far it is between subsequent dots. And so here we see that this student was moving, at a moderate pace for, a few hundred meters here, or almost 200 meters, and then the student slowed down for a couple minutes, and then the student sped up and was going at a faster pace for the last, 3 minutes, it looks like. Okay, so we've got 3 minutes of moderate pace, 3 minutes of slow pace, and then 3 minutes of a higher pace. Okay. Well, I wonder if we couldn't make a graph out of that might be a little bit more informative. So here we're going to plot these points, all these different points, on a graph. And notice here we've got position here and time here. I call this a position versus time graph. And so anytime we say something versus something else, the first something is on the vertical axis and the second something is on the horizontal axis. So a position versus time graph has position on the vertical axis and time on the horizontal axis. And you can see that what we've done is we've just taken these dots and transferred them down. At t equals 0 minutes, the student was at 0 meters. At t equals, 1, 2, 3, 4 minutes, the student was at almost 200 meters. 1, 2, 3, 4 at about 200 meters. Okay, so we've just transferred these dots down onto this graph. And, well, we can get a real sense of the motion here, too. It's a little bit different from this, right? But it turns out that this has all of the information that the motion diagram has, but the position versus time graph actually has even more information. So these are dots. What we've done is we have shown where the student was at each of these specific times. Now we could take it a step farther and we could connect those dots, and now we really can get a sense of this motion. The continuous curve shows the student's position at all instants of time, not just these selected moments. Here we see position versus time. Okay, so now we've made a position versus time graph. And maybe you think that this is not that much less useful than this. It turns out that this position versus time graph is very, very useful. Why? Because the slope of a position versus time graph is the velocity. And let's go back and see if this just sort of intuitively makes sense. Looking at this graph here, where is the slope the greatest? I hope that we agree that the slope is the greatest between 6 and 10 minutes. And where is the student moving the fastest? Between 6 and 10 minutes. Where is the slope the least? Well, right here in the middle. Where is the student moving the slowest? Right here in the middle. And so we see here that how steep this line is helps us understand how quickly the student is moving. And that is a general rule. It doesn't just apply to this situation. In general, the velocity is the slope of a position versus time graph. Recall that the slope is rise over run. Looking back at this graph, our rise would be how far did the student go, And our run would be how long did it take for the student to get there. So our rise over run should be a change in position over a change in time. We call this velocity. So if we're in the x direction, it's delta x over delta t. If we're in the y direction, it's delta y over delta t. But either way, velocity is the slope of a position versus time graph. Let's do a quick example. You leave the classroom at 2 meters per second and walk for 5 seconds. I forgot my notebook. So you jog back to class at 5 meters per second for 2 seconds. Sketch a position versus time graph for the event. And then when we're done with that, we're going to sketch a velocity versus time graph for the event. So position versus time, our position should be on the vertical axis and our time should be on the horizontal axis. Let's just go ahead and call this x and we'll call this t. Well, if I leave the classroom at 2 meters per second and walk for 5 seconds, and then I realize I forgot my notebook and I walk back for 2 seconds, that means we need a total of 7 seconds here, don't we? We need a vertical scale here. How about 2, 4, 6, 8, 10, and these are meters. Okay. So 2 meters per second for 5 seconds. So after 1 second, I will be at 2 meters. After 2 seconds, I will be at 4 meters. And so on. After 3 seconds, I will be at 6 meters. And after 4 seconds, I will be at 8 meters. After 5 seconds, I will be at 10 meters. Okay, so there we go. And then I turn around and I walk at, or jog 5 meters per second for 2 seconds. So this is, I better label this 1, 2, 3, 4, 5. And then I go 5 meters per second for 2 seconds. So that means that after 1 more second I'm here, and then I'm back to where I started. Okay, so there is my position versus time graph for that event. Now let's make a velocity versus time graph for this event. So on the vertical axis, we'll have velocity. And in the horizontal axis, we'll have time. Again, we'll give ourselves the same scale here. Going out to there, so 1. Okay, there we go. And on the vertical axis, we've got velocity. And it looks like I left the classroom at 5 meters per second, or at 2 meters per second. I left the classroom at 2 meters per second. So that's going to put me right here. This is velocity in meters per second. We have 2 meters per second up until 5 seconds. So if this was positive away from the classroom, then towards the classroom must be negative. And so we must have to be down here, right? And so let's graph our negative 5 meters per second for the final 2 seconds right here. And in order to show that this jumps straight to there, we could do a little dashed line. You wouldn't necessarily have to do that, but I think it makes it a little easier for the eye to follow. I guess the last thing I need is a sense of scale here. Let's remind people that this is negative 5 meters per second, and that this up here is 2 meters per second. Okay, there we go. I sketched them. And when you see this word sketch, this is what we need, right? You don't have to get out your ruler. It doesn't have to be perfect. But what does it need to have is the correct shape, axes labeled, a scale, units. But I didn't get super worked up about making it perfect, but I get a real sense of what's happening. Okay. Now, let's see, does this jive with what I was just talking about? The slope of the position versus time graph should be the velocity. And indeed, that's what we see here, right? And so notice that this is the slope of this. In this case, I have graphed the slope of the position graph, I have graphed that right here, right? So we see a positive slope here, moderate positive slope, and then a larger negative slope. A moderate positive velocity and a larger negative velocity. Again, velocity is always the slope of a position versus time graph. All right, let me ask you a few questions about this idea. Here we see a graph. Notice this is position versus time. Which of these points, A, B, C, or D, has a positive velocity? Pause the video and see what you think. Okay, well, we're asked for velocity. Notice this is a position versus time graph. I see that the velocity is positive at point D. Why is it positive at point D? Because the slope is positive at point D. So notice I did leave E off of this list. E also has a positive slope, therefore a positive velocity. A real common incorrect answer I get is A. Notice that A has a positive position, but it has a negative slope, therefore a negative velocity. The correct choice is D. Here's another one. Where is the velocity negative? Attentive listeners will notice I just told you the answer. Pause the video, see what you think. Okay, where is the velocity negative? We're looking for a negative slope. I see a negative slope at B and at A. Notice I did not give you A on the list. The only one that has a negative velocity is point B. Again, commonly, students will select either B or C, but the position of B and C is negative. However, the velocity is only negative at B. Where is the velocity 0? Hopefully you chose C. C is where the velocity is 0 because the slope is 0. Again, a common answer here is D, but that's not correct. The position is 0, but the velocity is not 0 at D. So we see here that we can have a position that's positive, negative, or 0, while simultaneously having a velocity that is either positive, negative, or 0. Right? Are the two things related? Yeah, but just knowing the velocity doesn't tell you the position, and just knowing the position doesn't tell you the velocity. You need a little bit more about it. You need to know how the position is changing in order to know the velocity. Okay, where is the position positive? Hopefully you chose A. The position is positive at A. Notice E also has a positive position. Where is the speed the greatest? Pause the video, see what you think. Well, remember that speed is the magnitude or the size of the velocity vector. And in this case, we are in one dimension. So our direction of our velocity is either positive or, got turned around, is either positive or negative, right? So that's how we decide the direction is positive or negative. So speed should be the absolute value of a velocity, or sort of how big is the velocity ignoring positive or negative. And so here we see that this is steeper than this is. So even though E has a positive velocity and D has a positive velocity, A and B have negative velocities. Since the magnitude of the slope is greater at A and B, that is where the speed is the greatest. Again, speed is the magnitude of the velocity vector. Here's another one. Here is a motion diagram of a car moving along a straight stretch of road. Which of the following velocity versus time graphs matches this motion diagram? Pause the video, see if you can't figure it out. Well, let's see. It starts off with a low speed, and then it jumps up to a higher speed, doesn't it? But I don't see a changing velocity here. This looks like, to me, a constant lower speed, and this looks like a constant higher speed. So let's look through these. A. Could it be A? Ooh, you know what? I think A is actually a graph of position versus time, right? In the beginning, he's moving fairly slowly until he gets a little ways from, I don't know, his house. And then he goes a little bit faster, right? And then he moves a little bit faster here. So I think A is a pretty reasonable diagram for the position versus time graph. But we're asked for a velocity versus time graph. Not that one. I'm not sure what that could be. Ooh, how about this one? Here we see a lower positive velocity, and then it immediately jumps to a higher positive velocity. Ooh, I like that one. D says that it was not moving at all for a little ways, and then it had a constantly increasing velocity. Definitely not D. I think it's got to be C. And indeed it is. Again, this then is the position versus time graph, and this is the velocity versus time graph. Okay, now let's give just a position versus time, and which one of these velocity versus time graphs matches this? Okay, well, let's see. What should we be looking at? Notice here in this segment, what's the slope? 0. Therefore, the velocity must be 0. So we're looking for a graph that has 0 velocity for a while, and then changes. This one starts out at non-zero, so it can't be that one. Looks like B, C, and D all start with 0 velocity. It could be that. Let's see what happens after that. Okay, so we have a 0 slope for a minute, and then we have a negative constant slope. So we should be looking for a graph that starts out at 0 and then jumps to some negative value but doesn't change. I only see one that looks like that. It is C. And indeed, C is the correct velocity versus time graph that matches this position versus time graph. Notice that we know this because C is the slope of this graph. Let's see if we can go the other way. Here is a velocity versus time graph. Which one of these position graphs matches? In other words, for which one of these position graphs is this the slope graph? Pause the video, see if you can't figure it out. Okay, so let's see here. Velocity, we should be looking for something with a positive constant slope that's starting off with a positive constant slope, right? So the slope should be positive and constant. Ooh, this starts off with a slope of 0. This one starts off with a positive constant slope. Okay, I like that. Let's. Ooh, this one starts off with a slope of 0. It can't be that one. This one starts off with a positive constant slope. Okay, it's definitely B or D. What does it do after that? So positive constant slope and then jumps to a 0 slope. Ooh, well, let's see. This one also has a 0 slope. So does this one. Which one is the best choice? Well, if this was our best choice, then we should have seen a very, very large negative velocity for just a moment as this object went right back to where it started. We don't see that. Our best choice is definitely D. And we can also distinguish between D and B by the words here. A graph of a velocity versus time for a hockey puck shot into a goal appears like this, right? And so, looking at this is a hockey puck. It cruises down the ice, and then it hits the goal, and it stays there. What if this was it? Cruises down the ice, and then immediately returns back to the player who shot it. That doesn't make any sense. That's not what hockey pucks do. Okay. Let's do another example. A car travels at a constant 12 meters per second for 4 seconds. Draw a velocity graph. Okay, I can do that. So, I didn't say velocity versus time. I probably should have. We should interpret this as a velocity versus time graph. For 4 seconds. 1, 2, 3, 4. 12 meters per second. Oh, 3, 6, 9, 12. This is velocity in meters per second. Okay, we're going to draw our velocity versus time graph. Car travels at a constant 12 meters per second. I can draw a constant graph, right? It just is a straight line, right? Okay. There we go. Woo! Okay. Great, I did it. Okay. How far did the car travel between 1 second and 3 seconds? How far did the car travel between 1 second and 3 seconds? Well, let's remember our equation that says that the velocity in the x direction is delta x divided by delta t. Well, it said, how far did the car travel? Change in position is what we're looking for. So we could do some quick algebra here, and we could see that delta x is equal to v sub x times delta t. So plugging in our numbers, we get velocity as 12 meters per second times delta t. Well, delta t, that's t final minus t initial. Well, 3 minus 1, that's 2 seconds, right? So this is for 2 seconds. 2 times 12 is 24 meters. Okay, not too bad, right? Not too bad. Let's look back up at our graph, though. Notice that we are looking for how far did the car travel between 1 second and 3 seconds. Okay, so between 1 second and 3 seconds. Well, let's just shade this area here. Let's find the area of that triangle. That's not a triangle. That's a rectangle type object. Okay, so there we go. There's my shaded area. Let's find the area of that area. Okay, area is totally base times height of a rectangle kind of an object, right? So area equals base times height, and so this is has a base of 2 seconds, and it has a height of 12 meters per second. By golly, our seconds cancel, and we ended up with 24 meters. Oh. Well, if that isn't just the exact same thing that I got down here. Well, what does that tell us? It actually tells us that the area under the curve of a velocity versus time graph is the distance traveled. So we can get a velocity graph by looking at the slope. The slope of a position graph is the velocity. But if we have the velocity graph, we can figure out the distance traveled by finding the area under the curve. And what do I mean by the area under the curve? I mean the area that is between the graph and the curve and the x-axis. That's what I mean by that. The area between the curve and the x-axis. That's what I mean by the area under the curve. Those of you that have had some calculus will recognize this as an integral, though I promise not to use the I word again. Okay, so most of the graphs we've talked about so far here, they kind of have this shape, something like this. At any rate, they've been a series of straight lines, but that's not really how most objects move. Like, for example, imagine a car that's accelerating away from, a stop sign or something. A car would be going slow in the beginning and then faster as it went along, right? And so you can see here that on this graph, the slope does increase, right? Here we see a slope of almost 0, which makes sense. It started from rest. And then the slope slowly increases as the speed of the car increases. So this is a much more realistic graph of what an actual object might do than those ones we were looking at a minute ago. If we were to look at, 2 subsequent dots here, we'd see that in the same time interval, we see a much greater change in distance. Same time interval, greater change in distance. And so we say, yes, definitely, the speed is increasing. the velocity is increasing. And so we need to use this idea of the instantaneous velocity. And so the instantaneous velocity is the velocity at any instant. If you're driving along and you look at your speedometer, that's giving you the instantaneous velocity, right? You can go 60 miles an hour without driving either 60 miles or for 1 hour. So instantaneous velocity is just how fast am I going right now, or at some other instant. And from now on, if we just say velocity, then we're talking about the instantaneous velocity. If we're talking about average velocity, then we will use that qualifier and we will say average.